Thank you, Avi. So let's start with a very simple warm-up question. So suppose we have n real numbers, s1, s2, up to sn, and we know the sum is non-negative. Then we call a subset to be non-negative if the sum of its elements is non-negative. Now the question is, what's the minimum number of non-negative subset? Actually, here I need a subset to be proper. So basically, I want to exclude the empty set. Can anyone give me a quick answer? So you want to minimize the number of non-negative subset over all possible choices of real numbers s1 up to sn whose sum is greater than or equal to 0.
So 2 to the n minus 1?
Yes, exactly. So the answer is just 2 to the n minus 1. And to show this can be achieved, we can just take the first number to be n minus 1, and for all the other numbers to be minus 1. The sum is equal to 0, and if a proper subset has non-negative sum, it must always contain s1. So half of the subset is non-negative. And also we can show it's at least 2 to the power of n minus 1. The reason is we can just take a subset S and pair it with the complement of this itself. So you get S and S complement. And we know the sum for the elements in S plus the sum of the elements in S complement, so S. This is just equal to the sum of Si, which is greater than or equal to 0. So at least one of them must be non-negative. So at least half of the 2 to the n subset must be non-negative. So now I'm asking a new question. So what happens if we look at only the subset of fixed size? So here I defined A of nk to be the minimum number of non-negative subset of size k. So in the future, I will call such non-negative subset of size k to be a non-negative k sum. Over all possible choices of s1 dot sn whose sum is greater than or equal to 0. So is everybody clear with this definition? Oh no, they're all real numbers. So over all possible choices of reals. That's a good question. So I guess it doesn't matter because maybe we can reduce the real problem first to rational numbers and then multiply them. Okay, so if we still take the same construction, we can see what's the number we can get. So example is we still take s1 equal to n minus 1, and the other numbers equal to minus 1. Then in order for a non-negative k-sum, in order for a k-sum to be non-negative, we must always use s1, right? Because all the other numbers are negative, strictly negative. So the answer is n minus 1 choose k minus 1. So we can show that ank is at most this number. Because for non-negative k-sum, you must choose s1 and then pick k minus 1 numbers from the rest of them. Now actually, there's a conjecture back to the 80s by Manickam-Mikl and os-Singhi. They asked, is it true that ank is always equal to n minus 1 k, choose k minus 1 for n greater than or equal to 4 times k? I will explain why we need this condition later. And actually, this comes from their study of some invariant of association scheme, but I don't know what that exactly is. But at least this conjecture itself is so beautiful, and very innocent looking. And this
is supposed to be true for any sequence x.
Yeah, for any sequence. So you want to show that for any sequence Si, this number is always greater than or equal to n minus 1 choose k minus 1. So I just minimize the number of non-negative k sums. Yeah. Okay, so first, I think this conjecture might remind you about a very famous theorem by Erd H. It can be somehow regarded as an analog of it, although we don't know the relation between these two results. So the EKR theorem says that the maximum intersecting family of subset of n actually is K subset, has size at most n minus 1 choose K minus 1 when n is greater than or equal to 2 times K. Sorry? Intersecting family is every 2 subset intersect. And the example is just very similar. So we just take all the K subset containing the first element, for example. Then we get n minus 1 choose K minus 1. And because all of them contain 1, so the intersection always contains 1. And now you can also ask, what happens if we don't restrict the subset to be uniform? So what happens if we just want to have the maximum intersecting family of subset of n? Then the answer is, again, 2 to the n minus 1. Because you can take all the subset containing 1. And to prove this is a lower bound, you just do the same trick. You take a subset with complement. At least one, at most one of them actually must be in this family. Now here, because you know that we're maximizing it, right? Mm-hmm. And so, but
by the way, so this EKR theorem.
Yeah, this is.
I mean, it's also it's also related to this Chauffeur-Ray-Wilson type of thing too, right?
You mean when this is not uniform, right?
Yeah.
I think the result is
because,
like.
For example, all pairs have to intersect in between 1 and k, or actually 1 and k minus 1.
Yeah, they get something like n minus 1 choose maybe k minus 1 plus.
Constant in front, but I think
Some result like this. I think the proof is like using some polynomial method. You look at some polynomial space and say the dimension of this and most equal to something. Right. And then, okay. So let's go back to our problem. So now I'll explain you why this is. You need to have this n greater than or equal to 4 times k. So remember that in Erd H, you can always take. You can also take a clique. So you can just take all the k subset. If n is less than or equal to 2k minus 1, then all these subsets automatically intersect by kind of, because 2k is greater than 2k minus 1. Right? So similarly here, so instead of, for example, for Manickam-Mikl and os-Singhi, instead of taking S1 equal to n minus 1, you can take S1 equal to minus n minus 1. So here you will get 2k minus 1 choose k minus 1, choose k. And this is greater than n minus 1 choose k minus 1 if n is too small. Just a different kind of construction. But there's not enough space to fix two different subsets. So yeah, so now I can also change the sign of the sequence. Now the sum is still greater than or equal to 0. Now the non-negative k sums use only S2 to Sn. So the number of non-negative k sums in this case is equal to n minus 1 choose k, right? And this number is greater than or equal to n minus 1 choose k minus 1 if n is too small. So for example, n less than or equal to 2k minus 1 or something. I don't know the constant. And actually, we can push it even further. You can take S1 equal to you can let n equal to 3k plus 1, s1 equal to minus 3k minus 2. As I take 3 copies of negative 3k minus 2, and all the rest to be 3. And there are 3k minus 2 copies. The sum is still equal to 0, and there are 3k plus 1 numbers. And if you compute the number of non-negative k-sums, you can see in order for the k-sum to be non-negative, you must always use 3 plus 3 plus 3, right? So it's like 3k minus 2 choose k. And you compare this with, let me see. So it's m minus 1 choose k minus 1, 3k choose k minus 1. And if you expand this and cancel the terms, you will see this is true when k is large. And if you want to repeat this, so
And the fact that n is in the MS example, why did you use the fact that n is the sum of 2k minus 1?
which one? This one, right? This one? Because I want this number to, I'm saying that if n is less than or equal to 2k minus 1, this example will do better. So here, if you take k to be large, this example will also beat the conjectured bound. But you're saying that it's not like 4k minus 3? Or?
Some subsets of the 3.
I want the sum to be 0, and
You could potentially have more than a negative one, right?
but then I have too many here.
You want to minimize the number of k subsets.
I want to
The
minimize.
problem is that there are too many k-sets, which in this example, which are non-negative. So it would violate the conjectured bound of less n is.
I'm explaining why we have this n greater than or equal to.
Find the minimum number, right? Find the maximum one, should also be 1. Right? Then you will in a negative pattern. All kinds of
Over the worst example.
But the worst will have the minimum number, not the maximum number.
Yeah, so in this
Yes.
example, you have to find the minimum of the whole example.
Yes. In this example, I don't see why it's 3k minus 2 choose k, because we choose more sets of size k.
No.
Right, so 3k minus
No, if you can pick minus 3k minus 2, then you have like 3k minus 3 for the other k minus 1 number, then the sum is less than.
Would you
Zero.
explain again how this example is constructed? You have 3 sets of size, 3 variables,
So
times 3k minus 2.
yeah, so I have 3 numbers minus 3k minus 2, and then 3k minus 1 3s.
Okay.
And the sum is equal to 0. And if you have a non-negative k-sum, all of these numbers in the k-sum must be 3. So basically picking the numbers carefully such that, the non-negative k-sum only use the positive numbers. And these numbers are as big as possible, as small as possible.
So this, okay, so what you're saying is any case set with k, but then, okay, so this proves that n must be at least 3k plus 2, but,
Yes.
okay, so we still haven't gotten to 9k.
Yeah. So you can repeat the same construction for example, 4k minus 3 for 4 copies, and then 4 here. But then if you compute the binomial coefficient, you will see this number no longer beats the n minus 1 choose k minus 1 bound. The reason that this is greater is because 3 squared is greater than 2 cubed. And if you do it for the next level, you will see 4 cubed is less than 3 to the 4th. So basically, there are 2 types of extreme examples. One of
So
them,
you can push it arbitrarily close to 4.
I don't think so. I think the best example we know is like 3k plus 1. I don't know if you can get like 4k minus 1 or something. Okay, now I have explained why this is n greater than or equal to 4 times k. Well, we can forget about 4 for a second. You can just think, is it true for like some constant times k? I mean, this doesn't make this problem become easier. So Now let me say a few words about what is known about this conjecture. So the first case is when n is divisible by k. And this proof is actually very beautiful, and I will explain it in just a few minutes. And
so by the way, is it clear, so I mean, at least asymptotically,
oh, asymptotically we
bound
know it,
will
yeah.
look like n to the k-1.
Yes, it comes from this case.
No, what I mean is that already known?
Yeah, it's already known. It just comes from here, you see.
Okay.
If we know it for k, 2k, 3k, and so on, then between them, I mean, it's asymptotically true. And
Sorry, why? Okay, why
Well-
we know it for k dividing and we know it symptotically?
yeah, we know
I mean, how does this imply that symptotic? It could be that this is.
I mean,
Yes, but it could be that this for
For
only
very
for
hard
those
case,
cases
none of fixed k and look at the very hard n.
yeah.
You know, they explain this exponent.
I mean, as long
Just explain the binomial.
And what I'm saying is that could be that the limit does not exist at all.
No,
that-
asymptotically means that you know the right, it will be n minus 1 plus k minus 1 times 1 plus 0, 1.
I think you know it's true for a dense subset of the integers. So this should be fine.
So what you're saying is
I
that
mean, you use the best bound available to you from this
I
case,
see.
right?
So if n is between 2k and 3k,
No, you just
But in your case, you do it here.
there's any case great.
okay, meaning okay. So what you're saying is that if we take k to be okay. So if we take k, this if we take sets of okay, if we take the sets n minus 1, k minus 1, then we still
Actually, I should say a few words, so it's not so obvious. So if you have S1 plus Sn greater than or equal to 0, then you can truncate it somewhere, and the first, let's say, t numbers still have non-negative stuff. So using this, you can show the n is greater than or equal to, here, this is some number which is smaller than n, but it's a multiple of k. This will give you asymptotics. I guess this is all right? Okay. So we also know the Manickam-Mikl single conjecture is true for k equals 2 and 3. This is done by Manickam himself and Chieslotti Marino in 2002. And this is probably not so difficult because actually we can show that if this result is true for n, then it's also true for n plus k. So essentially, we only need to check a few cases according to like the divisibility of 2 and 3. So then we know this is true for n very large. For n greater, these cases? No, I'm not going to show. I will show the first one. The first one I will show. This is by Manickam-Mikl 87. And finally, this is true for, well, not finally. So for n greater than constant times log k to the power of k. This is by Tiomkin in 2001. And as you can see, this number is still exponential, so you get e to the power of k log k. And what I'm going to show today is we can improve this bound to n to the power of some constant times k squared. So this is not as good as the linear bound, but still much better than all the previous exponential bounds. So this is by Along, myself, and Ben. So before talking about our result, first I want to say why this is true when n is divisible by k. So I'm going to show that a n k is equal to n minus 1 to k minus 1 when n is a multiple of k.
Where did this problem come up?
From some study of association scheme. Association scheme is like you're basically looking at the family of uniform subset, and you define the graph. The adjacency is based on the Hamming distance of this subset. and you want to study the eigenvalues and all the other things, but I don't know what they are doing exactly. So, okay. So first I want to mention the lemma by Beroni in 75. So if n is divisible by k, then if we look at the k uniform hypergraph on n vertices, which means you just take all the k subset of n, 1 to n. This can be decomposed as the union of matchings, and there are n choose k divided by n over k matchings. And let's see an example. For example, if you have n equal to 4, k equals 2. So basically, we are looking at a complete graph on 4 vertices, and we want to partition the edge set into disjoint matchings. So what we can do is, so I can, let's say 1, 2, 3, 4. So 1, 2, 3, 4 becomes the first matching. 2, 3, 1, 4 becomes the second one. 2, 4, 1, 3, the last one. So this is almost obvious. And if you want to look at n equals 2k, this is basically how you schedule a round-robin tournament for, I don't know, maybe football or chess. And even for k equals 3, it's not so obvious now. And the only proof that I know about this Beroni's lemma used some network flow method. So basically, you construct some flow, and then you use some flow. Mm-hmm. That's not Beroni. Just oh, so it's Baranian. Okay. I don't know how to pronounce the Hungarian names. It's not Imre Barani. Mm-hmm.
Wouldn't it follow some like this Einar's and everything?
No, it's a generalization concept. Although this is more exact.
Yeah, you want to have the exact version.
Yeah, this is more exact.
I think in order to get an asymptotic partition, it should be quite easy. But you want everything.
I'm sorry, so you took the clip and you partitioned it to matching?
Yes, for k equals 2. Mm-hmm. Yeah. So
It's a very it's just an example of a general statement.
I should tell you that the matching is just disjoint edges. So if for k equals 3, it's just disjoint triples. Mm-hmm. So you want to have like n, for each matching, you have n over 3 disjoint triples. No, it's just using the mass flow min cut to get the existence. We don't know the explicit.
But if it's using max flow min cut, how is it not?
No, it's explicit in the sense that you just spell out not for given for any n as a formula itself. K say this like
No, in the sense that you can, like this case, you can write out everything. Now, if we apply the Beroni's theorem for our application, then we can see we immediately prove this is n minus 1 choose k minus 1. Why? We just take this decomposition. And so for every matching, the sum is non-negative, right? So if we look at, for example, if we take a matching M1, let's say it's equal to E1 union En over k, that n over k edges, then the sum of this is just equal to the sum of Si, which is greater than or equal to 0. So at least one of these sums must be non-negative. Now let's count how many non-negative k-sums we have. So in total, we have n choose k k-sums. Now for every perfect matching, there are n over k edges. At least one of them will give you a non-negative k-sum, so it's 1 over n over k. And if you do the calculation, this is just equal to n minus 1 choose k minus 1. And this will prove the result for k n divisible by k. But if you try to use similar method, and this will not work when n is equal to, say, 4k plus 1 or something.
I mean, do you get an additive error? Or
Sorry?
do you get an additive error or a multiplicative error if you do this for
I mean, it's always additive error. I mean,
How do you choose the assignment to the variables?
It's a low bar.
Okay.
It's a low
the
bar.
assignment.
Yeah, you just need to show that greater than equal to this.
Okay, so how do you find the set, this number of subsets?
I mean,
Just say that if you have any set of numbers,
mhm.
just partition the subsets, the case subsets into these groups, and in every
Mhm.
matching you'll have at least one non-negative.
So in total, we have at least this many.
Because the total sum
Mhm.
is non-negative, and every matching is the sum over the sum.
Oh.
Just the sum of everything.
Right.
Everyone, it's a generalization of what he showed over there.
So I want to show a lower bound on the number of non-negative case sum. And here, this one is actually an upper bound. I mean this one. Mhm.
Sorry, I think I missed something very crucial.
Sorry?
I missed something very crucial. Like, what is capital K?
Where is capital K?
What is
Ah,
capital K?
This is like a complete hypergraph. So you can just think about as all the k subset of 1 to n. I don't know why dynamic k.
So, do any of these other proofs use any other techniques than the fact that if you have a
Mhm.
partition of the variables, that at least one of the sums must be non-negative?
I don't think. Well, you always use similar things, but I don't think they use the exact version of that. Mhm.
Okay.
Yeah,
For n is for n plus k.
yeah, it's the same technique. Mhm. Mhm. So if you want to do it for like 4k plus 1, you can still partition it, and then you have one element left. Then you can't really say anything about the non-negativity of this set. Mhm. I mean, if this is the smallest number, then you know at least one of them is non-negative. But what happens if this is the biggest number? Then you don't know about. Okay. So now we can think of this proof from a different perspective. So if we define the hypergraph H in the following way, such that if you look at the k minus 1 tuple, sorry, a k tuple, E is an edge in the hypergraph if and only if the sum of its elements is less than 0. Now we can see the condition that the sum of everything is greater than or equal to 0 just implies that there is no perfect matching. I'm always looking at the n divisible by k case first. So there's no perfect matching in k and k, right? Because if there's a perfect matching, then the sum is negative. Here?
0 and k and k, that should be h.
K and k. No? I think it's good. Sorry. H. K and k has a perfect match. Okay. Okay, so now the question will become like, if we know a hypergraph H has no perfect matching, how do we, so recall that we want to minimize the number of non-negative k sums. So here we want to maximize the number of edges.
So how many edges can you be missing to guarantee that?
Yes,
you have
exactly.
no perfect matching?
So what I'm trying to do next is try to also transform the original conjecture, not only for the case when n divisible by k, to this kind of problems and get some bound of it.
Can you go the other direction too? So given any hypergraph which is missing some small number of edges and yet has no perfect matching, does it imply the existence?
Let me see. So you said small number of edges. So the edges the number of edges missing is small.
Yeah.
So there are lots of
suppose you have a hypergraph missing less than a n k, edges. It's, k unit.
Well, actually,
Just ask if the hypergraph has no perfect matching.
I
Give it values so that every edge has a non-negative.
Yeah.
Yeah, actually, I was.
If and only if.
Actually, I will show that actually this ANK is precisely like this kind of problem you're talking about. It's equal. So both directions will be
It's
correct.
equal
Yeah.
because if there is no perfect matching, you can find like.
I can do something. But it's for fractional matching, not for matching.
Huh?
It's for fractional matching.
Okay,
I will
I
talk
mean, that
about-
argument works anyways with fractional matching, right?
Right. I will talk about it, but just don't hurry. So first I want to prove our result. The ANK is equal to n minus 1 choose k minus 1 when n is large. So here I get some constant, 33 times k squared, but we didn't try our best to optimize the constant. So let me see. Okay. So first we discuss two cases. But before that, I want to assume that the sum of Si is equal to 0, right? Because you can always decrease them a little bit. And okay. Now, I also want to assume that it's in decreasing order. This will not change anything. And there are two different cases. So first of all, we want to rule out the case where you have this this kind of structure. So basically, all the non-negative k sum must contain the first element. I want to rule out this case. So the first case is like when you have S1 plus the last k minus 1 numbers. This is from n minus k plus 1 plus 2 to Sn. If this number is greater than or equal to 0, then this automatically guarantees you n minus 1 choose k minus 1 non-negative k sums, right? Because you can just take S1 and any other k minus 1 numbers. Now I want to look at the second case. So we know this number is less than or equal to 0, less than 0. Now this will imply that the remaining n minus k number has a non-negative sum. So the sum from S2 to Sn minus k plus 1 is greater than 0. Then the trick is we can use the case when n is divisible by k to get.
Sorry, I don't understand this case too. X1, what? Okay. Okay.
The same thing. Yeah.
Okay.
Just, yeah. Okay. So now for the remaining numbers, the sum is greater than 0. Then I want to use the case when n is divisible by k to find many non-negative k sums only using the elements from S2 to Sn minus k plus 1. And then I claim that there are also lots of non-negative k sums using the largest number. And then if the sum of these two things is greater than n minus 1 choose k minus 1, then we can prove the result. Okay. So in this case, we know that the sum of this number is greater than or equal to 0. So how many numbers do we have? We have n minus k numbers. And now just pick t such that t is less than, well, less than or equal to n minus k, but t is divisible by k. Then we know the number of non-negative k sums from the set S2 to Sn minus k plus 1 is greater than or equal to, let's see, t minus 1 choose k minus 1, right? From the case when t is divisible by k. And you can always pick this t to be greater than or equal to n minus 2k plus 1. So this is greater than or equal to n minus 2k choose k minus 1. So we get a lower bound on the number of non-negative k sums using S2 to Sn minus k plus 1. And now if I call capital N to be the number of non-negative k sums involving S1. And if we can show that, so we want to show that n plus this number n minus 2k choose k minus 1 is greater than or equal to n minus 1 choose k minus 1, then we are all set. Now, basically, you want to compare n with the difference of these two numbers. So it's n minus 1 choose k minus 1 minus n minus 2k choose k minus 1. Here I will not do the calculation, but I will tell you that the asymptotics is just 2k squared over n times n minus 1 choose k minus 1. So if we, for example, we can show that there are at least, I don't know, 1/2 times n minus 1 choose k minus 1 non-negative k sums using S1, then we'll immediately get this conjecture is true for a quadratic range of n, and so on.
Replace every non-negative k sum in the x to x and minus k plus 1 with x1 and get k.
I guess you can do that, yeah, but it doesn't give you the.
So could you repeat the last sentence? Okay, so this difference on the right hand side is about 2k squared over n.
So if we can show n is very large, for example, I mean if we can show n is greater than some constant times n minus 1 choose k minus 1, this is the upper bound, right? Then we can get a quadratic range and something like this. Mm-hmm. Yes.
But can it help you somehow fix n to be not too large and somehow later?
It's a good question. I've never thought about this case, no. But yeah. But not too large, it means still greater than 4 times k. Right? Yeah. Mm-hmm.
So easier when n is large.
What you said that k times 4 is not much if n is large, it is much if n is small.
Now the question is, how do we estimate the number of non-negative k sums using S1? So what I'm going to do next is I define the hypergraph H. So this hypergraph is k minus 1 uniform on m minus 1 vertices. And an edge is in this hypergraph if you look at the sum of the corresponding variables is greater than, it's less than minus S1. So let me write it down. So the vertex set of H is just the set from 2 to n. And the edge set is just a k minus 1 tuple E of, sorry. And if you look at the, let's say I in E as I, this is less than minus S1. So this gives you a hypergraph. So in order to know the number of non-negative k sums, so this number is like n, right? So this n is just equal to the number of non-edges in this hypergraph, right? So if we want to prove that this is greater than or equal to something, we just need to show that the number of edges, so n is greater than or equal to something, is just equivalent to the number of edges is at most something. But how do we do this? So the next thing I want to introduce is the matching number and fractional matching number. And we can show that this hypergraph is not arbitrary hypergraph. Actually, the matching number and fractional matching number is at most something, like in the previous case we discussed. And then from there, we can get the number of edges is at most equal to something. And then we get a lower bound of the number of non-negative k sums using S1. It's slightly different, right? Yeah, because we look at K tuples there, and we don't isolate S1 like in this case.
I meant the ones like the log K to the K.
K to the K?
You had some previous results that were like K to the K and C to the K.
No, I think that's totally different with by some induction. It's not my result. So. So one obvious fact is that now we know our hypergraph is K minus 1 uniform on M minus 1 vertices. So we know the matching number. Maybe I should define what's a matching number first. So the matching number, nu of H, is just the maximum number of disjoint edges in the hypergraph H. So one obvious fact is the matching number is at most M minus 1 divided by K minus 1, right? There's nothing to prove. And actually, we can show that for our particular hypergraph constructed from the sequence of numbers, the matching number is at most N over K. Now, if you look at the constant before N, you can see this is slightly smaller. And this gap is already enough for us to get some bound on the number of edges. Any question? So to show this is very simple. So let's assume the matching number is nu of H. So we just have nu of H as disjoint edges. And if we look at the sum of the elements in this edge, then this is at most less than minus S1, right, by the definition. And you keep doing this. And then you can see how many numbers are left. So the numbers left is like M minus K times nu of, actually K minus 1 times nu of H, because every edge has K minus 1 vertices. So in total, we know the sum of Si is equal to 0. And this is bounded by, here we bound every sum here by S minus S1. And there are nu of H of them. And for the remaining vertices, we just use Si is at most S1, because we assume that S1 is the largest number. So this is just M minus K minus 1 times nu of H times S1. And if you solve this, you can see nu of H is at most N over K. And now the question becomes, if we know the matching number is like, cannot be very large, cannot be close to the maximum that it can be, then what's the maximum number of edges? So in order to do this, we need to introduce the definition of so-called fractional matching.
Will the fractional matching also be bounded by N over K?
Yes.
Okay.
Yes. Yeah, you're very quick, so actually I will talk about this maybe on this ramble. So now I define the fractional matching number. Nu star of H. So this number is just equal to, let me explain the idea first. So for the matching number, we just assign to every edge a number either 0 or 1, such that every vertex is covered by at most one edge. Now instead of assigning 0 or 1 to this edge, we can assign the real number between 0 and 1, such that for every vertex, the sum of the edges, the weight on the edges covering it is at most 1. So let me write it down. So we want to maximize. So first of all, we have a weight function from the edge set to 0, 1. And such that for every vertex, the total weight of the edges containing this vertex is at most 1. Let me see for every vertex. Now we want to maximize the sum of the total weight. The sum of the weight, so it's U of H. Yeah. Now as you can see, if we change this number to the set 0 and 1 is just the usual matching. Right? Now here I will not give a proof, but as Anchor suggested, we also have the same result for fractional matching number. So for our hypergraph, the fractional matching number is at most n over k. The proof is very similar. You just use this kind of idea, but for fractional matchings. Now, before estimating the number of edges, I need the last step. So I want to introduce the dual of this. So this is basically a linear programming. So for matching number, it's an integer programming, and this is relaxation. So it becomes a linear programming. And if we look at the dual problem, this will define you the fractional covering number. So it's dual LP. Tau star of H. So this is just defined as the minimum. Now instead of put the weight on the edges, we put the weight on the vertices. And we want to minimize the total weight on the vertices, such that, first of all, W is a function from the vertex set to 0, 1. And now for every edge, if you look at the sum of the weight on its vertices, then this number is at most 1. Right?
Most 1, right?
So at least 1.
At
least it's a covering. So we want to cover every, for every vertex at least once. So cover every edge at least once, yeah. And now by the duality of linear programming, we know that actually these two numbers are equal. It's the same thing.
Or, yeah, they're
I mean, it's the same.
Yeah, it's the same.
W and 1 minus W of B for each carrier.
Yes, it's the same thing basically. There's nothing particular about this result. So what we know now is that fractional covering number is equal to the fractional matching number. Can you see this? And this is just at most m over k for our k minus 1 uniform hypergraph on n minus 1 vertices. And now I will give a very quick proof of trend. So instead of showing you the quadratic range, I will show you this Manickam-Mikl Singhi is true for a cubic range. So greater than or equal to, let's say, 2k cubed. Maybe there's some lower order terms here. Just using the result here. So first of all, as I said before, I want to estimate the number of edges in this hypergraph H. So now we know the fractional covering number is at most n over k. So what does it mean? So the fractional matching number is n over k, at most n over k. This implies we can always find a weight function, just by the definition, from the vertices to 0, 1, such that, first of all, the total weight is at most n over k, right? And then for every edge, the total weight is greater than or equal to 1. Now to estimate the number of edges, we can just sum up the second inequality for every edge. So let's see what we get. So if we sum up 1 for every edge, we get the number of edges, which is E of H. It's bounded by the double sum here. Now, let's see here. So if we fix a vertex V is contained in at most m minus, so our hypergraph is k minus 1 uniform on n-1 vertices. So for every vertex, it's contained at most n-2 to k-2 sums. Right? So here, H is k-1 uniform on n-1 vertices. So every vertex B here is counted at most n-2 to k-2 times. Yeah. So here we have sum of B. Now this number is bounded by n over k times n-2 to k-2. Now recall that the number of non-edges is just the number of non-negative k-sums using S1. So this is equal to the number of non-edges. So it's greater than equal to n-1 choose k-1, which is the total number of edges in when this is complete, minus n over k. This is just some boring calculation, but you can see finally we will get this is n-1 choose k-1 times 1 minus n over k times k-1 divided by n-1. And this is equal to just n minus k divided by n-1 times k. So what I want to tell you is that when n is really large, this number is basically goes to 1. And then you can show this is greater than, let's say, 1 over k plus 1 times n-1 choose k-1. And if you remember, in the beginning, we want the number of non-negative k-sums.
I mean, you can actually plug it in more directly, right? Because you have that inequality you want, and the n-1 choose k-1 just cancel.
Yeah, I can say that. Yeah. So remember that we are comparing n with this 2k squared over n. So we show that n is greater than 1 over k plus. The density of the non-edges is greater than 1 over k plus 1. And so here, if we compare this with 2k squared over n times n-1 choose k-1, this is true for n greater than, let's say, 2k cubed. So now the question is, can we do better? Can we actually improve this lower bound? For example, can we show that the number of non-edges has at least constant density? I mean, the non-edges has at least constant density. Then this will give us a quadratic range. And, okay. So actually, there's very strong supporting evidence of this guess. Because there was a very old conjecture by Erd H on the hypergraph matchings. I see. So because our hypergraph H is k-1 uniform on n-1 vertices, so if you fix a vertex B and see how many edges can contain it, just here I have different parameters, so it might create some confusion. So
you only need to sound all the edges in E of H, not all the edges in G, right?
yeah, just E of H.
So can you get something from this? Like, what's that?
Right, but we don't know that. We don't know any seven. We don't know the degree. Yeah. Yeah, maybe if we assume the numbers are decreasing order,
not,
maybe.
That much different, right? Because I mean, that's about the sort of deficiency of the.
Right. I mean, even if you get like constant times, here you get constant times m. So where is it? Here you get constant, then it's still at most quadratic. So this method will not prove a linear range. So, okay. So this is one of the major open problems in hypergraph matching by Erd H in 65, I think. So if we have a hypergraph H, which is k uniform, and maybe I should use different numbers to distinguish them. Okay, I still call it H, but it's a general hypergraph, not the hypergraph I just defined. So it's I uniform on m vertices, for example, and the matching number is nu of H. Then the number of edges is at most the maximum of r times nu of h plus 1 minus 1 choose r, and n choose r minus m minus nu of h choose r. So it looks scaring at first glance, but actually the idea is very simple. So it just conjectures that if you fix the matching number, then the maximum number of edges is achieved either when h is a clique on these many vertices. So you can see this is the minimum number of vertices in the maximum number of vertices in a clique such that the matching number is nu of h. Right? Clique. Or this one is basically the complement of a clique. So here you can think of it as you have a set which has size nu of h, who is a subset of the vertex set, and every edge must intersect with this set. Now you can see, because if you have a nu of h, the matching number to be nu of h, then there are nu of h disjoint edges, but you can't have nu of h plus 1, right? Because if you look at the intersection, they're also disjoint.
Should we choose r minus 1 for that?
Oh, just r.
It seems that we need to pick r minus 1 that sits outside of the conjecture.
No, it's just r vertices.
I mean, that's all of those, all of them except those that don't intersect.
Mm-hmm. So it's like, so we have this set nu of h. First, the total number of edges is n choose r, right? Then we look at the edges which is completely contained in its complement. So it's n of n minus this number choose r. So there's no r minus 1 involved.
Conjecture such a set of the complement is tight if n is large enough.
Yes.
Is this known? Asymptotic if n is large enough?
Yeah, it's known. Actually, I will talk about it in the second part of my talk, but let me finish the proof first. So if you just plug in everything into this Erd H conjecture, so remember that we have a hypergraph has n minus 1 vertices. The uniformity is k minus 1, and the matching number is at most n over k, right? So if we plug everything, you can see the number of edges is at most the maximum of, here I will not do a calculation too carefully, just show you what it roughly is. And here you have n choose maybe n minus 1 choose k minus 1 minus this number. And here, if I only look at the asymptotics, you can see this is like the maximum of this number is like so it's k minus 1 divided by k to the power of k minus 1. So here n minus 1 choose k minus 1 times this. And here this one is just 1 minus this. And this is like, when k is really large, it's like 1 over e. This is like 1 minus 1 over e. So basically here we will get the number of edges is at most some constant times n minus 1 choose k minus 1. From there, we will see this capital N is at least constant, constant times n minus 1 choose k minus 1. And this will give us the quadratic range. But unfortunately, we don't know whether this conjecture is true.
Wait, this would give you the quadratic range?
Yes.
Instead of, okay.
So here you will get just this is bigger than some constant c times.
So do you know the conjecture if you are bounded with facts?
I will know a lot about this conjecture, but I prefer to talk about it later. So something else. Okay. So, but there's another way to do it. So actually, if we don't look at the matching number, but we look at the fractional matching number, then we can estimate the number of edges more efficiently. So here I need to mention the result by Feiger. In 2006. So suppose we have some non-negative. The non-negativity is very important here. An independent random variable S1 as, let's say, as M. So basically, we know the fractional matching number, and we want to estimate the number of edges. We can transform this problem into the problem of finding the minimum probability that the sum of random variables deviate from its expectation by a small number. So this now our random variables has expectation at most 1. Now Feiger proved that if you look at the probability that sum of Si, where I is from 1 to m, this is less than or equal to m plus delta, then this probability is at least as large as the minimum of delta over 1 plus delta 1 over 13. So if you, for example, if you look at the case when m is equal to 1, so what does it say? If a random variable is non-negative and has expectation less than or equal to 1, then the probability that is smaller than 1 plus delta is at least delta over 1 plus delta. It's just Markov's inequality. So, and actually, Feiger conjecture that the extremal case of this problem is achieved in 2 cases. The first one is when S1 is equal to 1 plus delta with probability 1 over 1 plus delta and 0 with probability delta over 1 plus delta. And all the other numbers are equal to 1 with, well, expectation you take, so with probability 1. Now you can see this is just like in the Markov's inequality case. You get this delta over 1 plus delta bound. And he also conjectured that there can be another case which sometimes do better than it. So it's all the Si is equal to m plus delta or 0. This one is with probability 1 over m plus delta. And this is 1 minus 1 over m plus delta. Now, in order for the sum to be less than or equal, actually it's less than. In order for the sum to be less than m plus delta, so what we need is we need everything to be 0. Right? So the probability here is equal to 1 minus 1 over m plus delta to the power of m. And as you can see, this number, when m is really large, it doesn't really depend on delta. So it can be like, goes to like 1 over e or something. So here, we are not able to prove this result for like 1 over e, but Feiger is somehow able to solve it for some smaller constant, like 1 over 13. And this will be already enough for our application, because for our application, this will only change the constant before this quadratic range. How is this proved? It's by basically, so you can somehow assume that every distribution is discrete. And then you do some shifting on the weight. And then you reduce this problem to the case that every variable is concentrated at 2 points. Then it becomes some kind of optimization problem. You can solve it. It's actually a special case of a more general conjecture. If I have time, I will talk about it in the end. So, all right, so let's see how we prove. Ank is equal to n minus 1 to k minus 1 for n greater than or equal to 33k squared. So in order to solve this, we only need to show that the number of edges, so if a hypergraph is k minus 1 uniform on n minus 1 vertices, and nu of h is at most n over k, then the number of edges missing is at least some constant times n minus 1 to k minus 1, given that n is greater than or equal to constant times k squared. Then from here, and then we compare it with this 2k squared over n times n minus 1 to k minus 1, we get this bound. So I'll just prove this claim. Now, you remember that here, not only the fractional matching number is smaller than that, the fractional covering number is also smaller than it. So first of all, we have a weight from the vertex set to fractional covering number. You see, from the vertex set to 0, 1, the sum of the weight is at most n over k. And for every edge, the weight is at least 1. Now we can see if we have an edge, then it implies the sum of the weight is greater than 1. So conversely, so if the sum of the weight is strictly smaller than 1, then we have a non-edge. Now we can, so basically we can estimate that we can give a lower bound of the number of non-edges by the probability that you randomly choose a k tuple such that the total weight is smaller than 1. But we don't really know how to choose a random, here is k minus 1 actually, a random k minus 1 tuple. But we can transform it into a random k minus 1 multi-set. And then we can use Feiger's result. So here's the trick. Now we define our random variables S1 to S, let me see, Sk minus 1. All of them are independent. So IID, random variables. And every of them is equal to W of V with probability 1 over m minus 1. So we have a weight on all the m minus 1 vertices. Now we just take Si equal to the weight with equal probability.
What do we?
Sorry?
What do you think? Oh, it's a random vertex.
I pick random vertex, yeah, basically. S of I, actually. Yeah, I is less from 1 to k for every V. And this gives you for every I. Now, I claim that the probability that random, so let me see. So first of all, the density of the non-edges, as I said before, is bounded from below by the probability that here you take a random k minus 1 subset. Let's call it V1 to Vk minus 1. Then the sum of the weight is less than 1, right?
So in the quadratic range, anyway, the multiset will be a set.
Right, exactly. And now I approximate with this with a random k minus 1 multiset. By multiset, I mean there can be 2 elements in this set that are the same. And then this is exactly equal to the probability that the sum of Si is less than 1. Yeah, I is from 1 to k minus 1. And if we want to estimate the error term here, you can see this is at most. So what happened if there's an error term? It's like you have some Si equal to Sj equal to some W of B, and there are m minus 1 choices for this vertex, and there are k minus 1 choose 2 choices for this pair of random variables. So if you multiply them, and when n is sufficiently large, in particular when n is greater than, so I also need to multiply the probability 1 over m minus 1 squared, because this is the probability that they are both equal to certain weight. So if you look at this, it's like k squared over n. When n is quadratic, this is smaller than some small constant. It's not epsilon, it's 1 over 33 or something.
Could you explain again the first inequality?
The first inequality. the first inequality is, as I said, the non-edge. So if the so for this given weight, if the total weight is smaller than 1, then it's a non-edge. So this is greater than or equal to. I see. So now the nice thing about this is we can use Figer's inequality. So here I will not do the calculation, but basically here we know the expectation of each SI. First of all, SI is non-negative, and the expectation is just like 1 over n minus 1 times n over k. So we know the expectation. Then we can just plug it in and normalize these random variables and estimate the probability. Finally, we will show that the density of non-edges is greater than the minimum of n minus k over n minus 2n minus k and 1 over 13. And when n is sufficiently large, this is close to 1 over 2, so it's greater than 1 over 13.
So the only reason for the quadratic gap is the birthday problem.
It's not only the quadratic. But also, if you remember, we compare constant times n minus 1 to k minus 1 with 2k squared over n. This will never do better than the quadratic. Yeah. We try very hard to improve it to the linear range, but so far we have no success. Yeah. Okay, so basically now I already give you the proof of this result. So next thing I want to mention is this Erd H conjecture. And
at least, so you have it for two reasons, but for avoiding the paradox, like, does this, if you choose them without replacement, it's like, it feels very, usually when you choose things with replacement without replacement, you get very similar behavior.
right.
I mean, does this result not hold if you choose them without replacement from a set randomly? Is there a counterexample to this theorem?
By without replacement, what do you mean?
So I mean, suppose here what you're doing is you're choosing your distribution is each xi is like uniformly at random from some set
Right.
of weights. So suppose that I want to prove that theorem, but I have a set of weights, and I choose m guys uniformly without replacement. Does the theorem still hold? Like, or I mean, do you have a counterexample to the theorem if you choose them without replacement?
Actually, I don't know about this. Yeah.
I mean, I'm just wondering, like, how crucial is this use of it? Like, you use n is greater than k squared twice, right? How crucial is this use of it?
Let me see. Well, I think it's probably if you modify the proof of Figer's result, maybe it doesn't really matter. I think it's still true. It just doesn't help us too much. But you probably need to go to the Figer's proof, or maybe there's some clever transformation to solve the case with.
Looks like by this extremal example, the proposed extremal example has two different types of variables here, which only has one. Like, that extra structure makes this useful.
So, okay, so yes, I should keep going. So, next thing I want to talk about is what we know about this Erd H conjecture and its application to different areas of math and even some engineering problems. So let me change the parameters a little bit to what I'm used to. Here we still have nu of h, okay? So I assume h is k uniform on m vertices. So the maximum is like k, I say nu of h is at most t. So basically, we don't have t disjoint edges in our hypergraph. Now this one is kt minus 1 choose k. Now I'm just more used to this format. And minus t plus 1 choose k. Okay, the same thing. So this conjecture has been open for 50 years, but we know something about it. So the first thing we know is the case when t is equal to 2. So basically, there's no pair of vertices of edges that are disjoint. Yes, just Erd is Colorado. So actually, in this case, if n is larger than 2k, it's the second term that is the biggest. So you get n choose k minus, here plug t equals 2, you get n minus 1 choose k. So just n minus 1 choose k minus 1. And if you look at the example, it's just this, the same point pencil structure. And the second case that is known is when k is equal to 2. So basically when this is a graph. And this is done by Erd H and Galai in 59. Now again, this is in 38. So these two special cases are solved before this conjecture was asked. Right? That's how usually people pose a conjecture. So in this case, we want to know the maximum number of edges in a graph where the matching number is given. And the key tool in this proof is that there is a formula which will determine the matching number of a graph. The matching number is always equal to 1/2 times this one. Let me just write out the formula.
Is this the Edmonds-Galai formula?
I think the name is called Tart-Birch formula.
Oh,
but maybe that one is a more general
I
case.
guess the Edmonds-Galai is the decomposition.
Yeah, I did some search online. I want to confirm the name. Okay. So actually, it's very easy to prove one side of inequality because if you have too many order components, then you cannot have a perfect matching, or you cannot have a matching with large size. Okay. It's minimum over all the subset of V. Here, you look at the sum of the size of the subset plus the size of the vertex set, I mean the total number of vertices, minus. This one is when you remove the vertex set U. In the remaining graph, you count how many order components you have. But
So
all the
it's like,
components.
you know, so you can think of it.
With all the number of vertices, yeah.
It's like, you know, how many nodes could be matched? Well, if you're deleting U, I'll assume all of those are matched, and then, you know, sort of pessimistically.
I think one side of them is very easy to prove, but the other one requires some effort. So, and using this result, actually one can easily show that the number of edges is at most the maximum of these two. And if you want to do the same thing for, let's say, k equals 3, for 3 uniform hypergraph, then we no longer have such formula, unfortunately. And actually, if we want to determine the matching number of a graph, it's known to be polynomial. But if we want to find the matching number of a hypergraph, it's NP complete, I think.
What about for fractional?
It's the same. No, for fractional, it's linear programming.
No, I meant,
Yeah.
is there a formula along the,
For graph.
for the,
for-
you know, for the fraction
For hypergraph, I'm not sure.
matching of the 3 uniform?
I'm not sure. Maybe you can have a
I mean,
somehow.
quality gives you something, but it doesn't give you something as
Yeah.
nice as this, for sure.
Exactly. Yeah. So I think even for, if you look at the k uniform hypergraph, that is k partite, finding the matching number is already NP complete, I think.
3D matching, right? Yeah, 3D matching.
And like just about a few months ago, Franco claimed that he proved it for the case k equals 3, but he didn't publish the paper yet. And so instead of showing this is true for all the range of t when k is fixed, one also can try to prove it for a certain range of matching numbers. So the earliest such result is by Bolobas, Dakin, and Erd H. 76. They show this is true if the matching number is less than n over some constant times k cubed. And quite recently, we improved this result. So with Poisson-Rowe from CMU and Bentley Sudakov. For t less than n over k cubed.
That's fantastic, right? Because that's basically
say that if you fix t and k, then for sufficient large n, it's true.
Oh, I see. So it's far from a perfect matching, but it's
Yeah, for perfect matching, it will not be helpful.
But
Yeah. Yeah, sorry, I should have mentioned that when t is small, in particular when t is smaller than n over k plus 1, it's always the second example that achieves the maximum. But when,
You know it for perfect matches, that's probably
yeah, that's the same problem with Manickam-Mikl. Yeah, we don't know it in this thing. So we improved this bound to n over k squared, but I'm not going to talk about this. So as you can see, one can still hope to get like about n t less than constant times k. It still will not solve the perfect matching problem, but it can maybe help us understand all this conjecture better.
You can also hope for, asymptotically for all.
For asymptotically, it's no.
Asymptotically, it's no.
It's no. So I think it's by Franco. Yeah, that's a very early result by Franco. He showed that the maximum number of edges is bounded by t minus 1 times n minus 1 choose k minus 1, I think. So this will tell you the asymptotic, I believe. And this is actually very, very easy proof. You just use the cycle method, like how you prove Erd is Colorado. So I want to talk about a few applications of this Erd conjecture. So the first one is to hypergraph matching, maybe. To hypergraph perfect matching. So by perfect matching, I mean just perfect matching just means the matching number is n over k. Right? Now, there's a question asked by Dakin and Hargreaves. So now first we define the minimum d degree of the hypergraph H to be the, let's see, the minimum number of edges containing a D subset of the vertex set. So let me explain this definition. So for example, if you take D equals 1, it's just the minimum number of edges containing a singleton of the vertex set. So it's just the minimum degree. If you let D equals 2, it's just a minimum co-degree. And so it's nothing fancy. And the question is, you want to determine MD of Kn, which is the minimum number S, such that if the minimum D degree is greater than this number, then this hypergraph has a perfect matching. Yes, that's what I'm going to talk about next. So suppose you look at D equals 1. And k equals 2. Yes. Well, yeah, for perfect matching, I need to assume n is divisible by k. So what does it mean? So we want to find the minimum degree such that this hypergraph contains a perfect matching. So yeah, the answer is like m over 2 to n. And the reason is you can, for example, if the minimum degree is greater than n over 2, then by Dirac theorem, we know there exists a Hamiltonian cycle. And you just take half of the edges, and it becomes a perfect match. Okay, let's tell you. And in order to show this is the other direction, then we just take a complete bipartite graph with two paths almost equal but slightly different. So with one path, for example, saying there is n over 2 minus 1, the other path n over 2 plus 1. Now we can see there's no perfect matching because then these two paths are not equal. And if you look at the degree, the minimum degree is like n over 2 minus 1. And for this problem, we know a few different cases before. For example, we know d equals 1, k equals 3. And also for arbitrary k, we know it for d equals k minus 1. So what we saw is that actually this problem is solved if we know the answer to the Erd H conjecture. So D is just some constant between 1 and k minus 1, just some integers. I have sorry, I have to say, so I always assume that H is k uniform on n vertices. Yeah, I want to find the. Yeah, and even when you look at you want to find the degree condition for let's say 6 uniform hypergraph to have a perfect match, and this is unknown. We don't know the precise threshold.
Are there algorithmic versions of these results?
Sorry, say that again.
Are there algorithmic versions of these results?
I don't know about this kind of.
D equals 1 and k equals 3, can we find when the sufficient condition holds, can find a perfect match?
I don't know about the algorithm.
Dirac is algorithmic, but once
Yes.
you go to more
I don't know for
uniform hypergraphs, then actually there are some sufficient conditions which are not known to be algorithmic. Like there's this Hall or Honel-Haxel.
Like for 3 uniform, right?
Yeah, I mean even for and I think it's even open whether it might be yeah, Hall or
Aroni and Haxel. Yeah, I don't know too much about the algorithmic aspect of these problems. So what I'm going to say next is that actually we can prove that this problem is solved if the Erd H conjecture can be solved. So that's basically why this long list of all courses come from. So if Erd H conjecture is true, then this implies that we know the asymptotics of m sub d of kn is the maximum of 1 over 2 and 1 minus k to the power of k minus d times n minus d to k minus d. So the second example is, there are 2 different cases. The second example is basically the same as the second extreme case in Erd H conjecture. And the first one comes from some similar construction with this. The maximum of this times n minus d to k minus d, sorry. Didn't put the bracket. Yeah, that's the maximum degree because, yeah, just do the counting for d degree. And yeah, I will not talk about this proof. I mean, it takes maybe 2 hours. It says, I'm not sure actually, so.
Are there graphs which have like a constant fraction?
I know the question, but I think for our proof we can only show this asymptotically equal. Actually, I have never met Franco, but I have anyway. I have a paper with him. So. I think he's currently in Japan. Right?
Yeah.
I think he even played. Even. Yeah, it's very fun. It's not affiliated to any university or institute, and even he plays some role in a popular TV show in Japan. It's very fun.
You should have had more background on this.
Yeah, that's more interesting, I think. Actually, you can go to his website. His website is all written in Japanese, and he shows some picture of like catching a fish, and also maybe he sells his book on how to learn 11 different languages, and on his website. Yeah, it's funny that. It's funny that. So when we wrote this paper, actually we have no way to contact Franco. So every time we need to discuss something with him, we need to write an email to Rodo first, and then Rodo will send Franco an email. Otherwise, he might not reply to us. It's very funny. So actually, when he wrote this, I think when he wrote some paper like this case when k equals 3, he need to ask somebody else to type for him. So maybe that's why this is still unpublished. Yeah, yeah, maybe. Okay. So the second application I want to talk about is just the application to Manickam-Mikl and Singhi. So actually, if we can show this conjecture is true, this will also imply the Manickam-Mikl and Singhi. So let me remind you, it's like the minimum number of non-negative k-sum is n minus 1 choose k minus 1 for sufficiently large n. Well, not too large, so 4 times k is enough. And here I made a claim that a of nk, this is also proved in our paper with Noga and Benny. So this is equal to n choose k minus the maximum number of edges. Well, so it's basically the minimum number of non-edges. So in a k-uniform hypergraph on m vertices with fractional matching number less than or equal to m over k. So in other words, we can show that this problem can be transformed to this kind of hypergraph matching problem, not only for the case when n is divisible by k, but for all the other cases. And the proof is actually not so difficult. So first of all, I will prove this is greater than or equal to. So suppose I have n real numbers S1 to Sn whose sum is greater than or equal to 0, and that a and k non-negative k-sums. Now what I want is I want to construct a hypergraph H such that the number of edges is greater than or equal to n choose k minus a of nk, right? Then this will show this greater than or equal to. So to do this, first of all, we use a small trick. So we let si prime to be equal to si plus some small constant delta. So let me first say something. So first we can assume that every si is less than or equal to 1 over k, right? Because if it's too big, then we can just rescale it. We just multiply everything by a very small constant epsilon to make this number sufficiently small. It doesn't change anything about the non-negative k-sum. So now we assume si is less than or equal to 1 over k. Now I use some small constant. I add si to some small constant. Now what we can see is like, now if we have a non-negative k-sum, it becomes positive because you add this constant where delta is greater than 0. And the sum of, and for negative k-sum, if we pick a sufficiently small delta, then this can still be negative. And now the total sum is greater than 0. So our next step is we construct the weight of on the hypergraph. So W of V. So I will define the hypergraph according to the weight function. So it's called threshold hypergraph or something, but I'm not going to that definition. So W of V is equal to, let's say W of I is equal to 1 over k minus Si prime. Now this is the weight function on the vertices. Now first let's check actually the sum is less than n over k. So this is strictly less than. So I want to show that the sum is strictly less than n over k. And this is because if you sum up all these things, you get n over k minus the sum of Si prime. And now we know sum of Si prime is greater than 0, so this is less than n over k. So nothing fancy. And now if we look at the sum of the weight of all the vertices belongs to a certain edge, this is equal to 1 minus Si prime, where I belongs to the edge. Now, if we have, let's see. So this number is actually greater than equal to 1 if this edge E, if the set E corresponds to a negative k-sum, So what this tells us is that the number of non-edges is greater than equal to A of nk. And this shows the first direction. Any question? And for the second one, it's also quite easy. So just right here. So I want to show this is less than or equal to. So now I have a hypergraph H with rational cover, let's say W, such that the sum of Wi is equal to n over k, where I goes over all the vertices, minus some delta, where delta is greater than 0. So we know that the rational matching number is strictly smaller than n over k, right? So you can assume there exists a weight function such that the sum is less than n over k. And for every edge, this is greater than or equal to 1. Now we just define the sequence of number in the following way. So we let Si equal to 1 over k minus delta over n minus W of I is the weight on the ith vertex. Now, first of all, we need to check that the sum of Si is non-negative. So the sum of Si is equal to n over k minus, so here this is delta over n times n, so it's delta minus sum of Wi. We know this is equal, so basically we get this is equal to 0. Oh, maybe this is, okay, never mind. So this is equal to 0. And if you want a non-negative k-sum, where S is equal to k, this is equal to 1 minus k times delta divided by n minus the sum of Wi. But we know that for every edge, this number is greater than or equal to 1. So this is strictly less than 0 for every edge. So from here, we can see the number of non-negative k-sums is at most n choose k minus the number of edges. And that proves the second part. So basically, these two quantities are equal. So if you can solve out this conjecture for when t is like equal to n over k, then this will settle the Manickam-Mikl os-Singhi conjecture. But we know almost nothing about this case. We know a lot of information on the other range, but when t is very close to n over k, this 33 times k squared is the best that we know about. I think if you know the matching number, this is weaker than the matching number, I guess. But for matching number, the problem is when n is not divisible by k, it's not too good for us. I mean, you know what I mean, right? But for fractional matching number, I mean, this can be like arbitrarily close to n over k, no matter whether n is divisible by k or not. Oh, you can ask the same. It's, no, we don't know. Even the asymptotic, we don't know. Yeah. So for this one, when I say you know the asymptotics, I mean basically the asymptotic of this side, not on the other one. Because when n is really large, it's the other side. Right? So what I say is if you assume, you can assume that t is equal to, you fix k and assume t is equal to some alpha times n, then the asymptotics about the alpha we don't know about it. Okay, so the last application I want to talk about is the application to designing a distributed storage system. So the distributed storage system is the following way. So first of all, we're given a file f. So suppose we have a long file f here. So we want to cut it into many small pieces, and then we have several nodes. Let's say n1 up to nk maybe. Then we want to truncate this file and even make several copies of each part and then put them into the node. So we store them in this way such that whenever we need to retrieve the original file f, we only need to read the node and then recover the original file from the nodes we access. So interesting result that, so someone can show that, I don't remember who did this, so there exists a coding scheme such that, so basically whenever the total amount of information, the total amount of information in the node's access is greater than equal to the length of the original file, then we can recover the original file.
These are like fountain codes, or
Sorry?
This is like fountain code types of.
Yeah, it's code. It's not, so you need some coding scheme, not only just like make a copy and then put it there. So now there are two different kinds of models. About how you access this node. So the first one is by, let me see. So the first model is, you just take a, so let's assume there are n nodes, okay? So take a random R subset of the node. And the second model is like pick every node independently with probability p. And you might ask why we don't put all the file into the first node and put the file into the second node, then we don't need to do anything, we just access one node, then we can recover f. The reason is we often have some restrictions on the total amount of information that's stored in those nodes. So we often, so suppose we have xi bit of information.
You're allowed
I can put anything, yeah. I can put it in multiple nodes. Yeah, I allowed to do linear combination. That's why we need a coding scheme.
Yeah, but anyway, so what's the model exactly? You break up your file anyway, well, you precise.
And then I code them and then put it into the node.
So every node contains just a piece of the same size as the
It's not a piece of the same size. I need to do some coding.
Okay, so it's just not like found code, you put the
I-
sound, you put an exclusive also.
I
The
see.
size of information at every node
Mhm.
is the size of the piece of.
I see.
So you will do something else.
Yeah, there's something else. No, I'm not going to show like how to find this coding scheme. I just want to say how this is connected to this conjecture. So suppose we have SI bit of information in Ni. Then we often have the restriction that the total information is less than or equal to some budget T. In real application, this budget can be like the storage space, or can be like when you do some network, it's like the bandwidth of the network transmission. So now what we want to do is we want to maximize the probability of successful recovery. So basically, we have a file f, so we don't really care about what the file is. We know the length is equal to 1, for example. And we want to find the values of Si. Si denotes the amount of information stored in the node Ni. And if we take we want to maximize the probability that a random R subset contains more information than the information in F. Then you can see this is basically the same as the Erd conjecture for fractional matching number. So if we can solve the Erd conjecture, we can help the engineers to find the optimal data allocation for the distributed storage system. But we don't know too much about the second model. Like how do we find this optimal allocation? So I guess I have not too much time left, so I will just mention a few open problems. So the first one is like proof Manickam-Mikl Singhi conjecture for the range n greater than constant times k. So as I said before, our method will not work for two reasons. The first one is when we apply the Feiger inequality. But I think that's not a big issue, because when you estimate error term, maybe you can somehow modify Feiger's proof and prove the probability is still greater than constant. So that's not a big problem. The big problem is when we look at the number of non-negative k sum, even if we have involving S1, even if we have n minus 1 to k minus 1, some constant times this, and when you're comparing with 2k squared over n, this will not help us too much. I mean, even if this is 1. We still get at most 2k squared. Yeah. And the second question I want to talk about here is, can we improve the bound in Feiger's conjecture? So Feiger conjecture is like you have random variable Si greater than or equal to 0, independent. Expectation is at most 1. So what's the minimum probability that the sum of Si is greater than some? It deviates from the expectation by at most delta. Less than or equal. Less than or equal to, yeah. So can we improve this 1 over 13 bound? So there's a question, and actually it's a special case of a very interesting conjecture by Samuels, but actually not so many people know about this conjecture. The conjecture comes from probability. So suppose we have a sequence of random variables S1 to Sn. All of them are non-negative, they're independent, and the expectation of each xi is known to be mu I. Now he asks, what's the minimum of the probability of when the sum is less than 1. So here, in order for this question to make sense, we need a sum of mu I to be greater than 1. Otherwise, you just take everything equals mu I, and this will give you 0. Right?
Why is K and N? Why did you use
N and N, sorry. So he actually conjectured that this is achieved in, maybe use a different ball, maybe. That's probability 1 over n? No. You need the expectation to be mu I.
Yeah, exactly. So it's 1 with probability 1 over. So all the mu i's are 1 over n.
No, but you can, the mu I is fixed.
The mu I
Yeah, I fixed. Yeah, I have to say that. And mu I is given, n is given, and you can pick the random variable by yourself. I want to get. No, I need a sum to be greater than 1.
Yeah, but if the sum is larger than 1, this could be, then this could never happen, right?
No.
What the xi are fixed, then the probability is 0.
I mean, yeah, something doesn't parse.
Maybe you want the max.
Let me see.
So all the xi is equal mu I following 1.
Yeah.
And you want an upper bound on this problem.
Let me see. So for Markov inequality, you get upper bound. No, this one we want.
Maybe you want summation mu is less than 1.
I want the summation to be less than 1, right? Oh, I see. I know the question. Let me see.
Maybe you want the expectation.
Let's see, maybe. So for
I've always said
oh yeah, this is less than 1. Sorry. Yeah, okay, it's less than 1. So, yeah. So sum of mu I is less than 1. Right, so, yeah. Yeah, for example, for Markov inequality, we need mu to be less than 1, otherwise it's always 0. Right? The minimum.
And you want to prove that the sum is smaller than the expectation? Or
No, just 1. Just 1. For small expectation, you can always get very close to 0.
The sum equals 1.
No, the sum is less than 1. I want to minimize the probability that the sum is less than 1. That's the question. And it's conjectured that the minimum is achieved by many different cases, but it's all like this. So S1 is equal to, let's say, 1 with probability mu1 and 0 probability 1 and mu1. S2 equals the same thing here, and so on. This will give you, so this probability, this event happened only when everything is equal to 0. So this will give you 1 minus mu1 times 1 minus mu2 times 1 minus mu n. Okay. And you can also.
Sorry, it's not going to be minimized when the sum of the mu i's is equal to 1?
It's less than 1.
No, but if it can.
Mu I is given, so. Okay, so but maybe there are some other cases. So it can be like S1 is always equal to mu1, and S2 is equal to 1 minus mu1 with probability mu2 over 1 minus mu1. This is something. And S3 is equal to 1 minus mu1 or 0, and so on. So this will give you just now S1 is always equal to mu1, so everything else must be 0. So it's 1 minus mu2 divided by 1 minus mu1 times 1 minus mu n divided by 1 minus mu1, and so on. So if you, for example, if you assume mu1 is in maybe increasing order, I don't remember, then it's always better to pick it like this rather than you take S2 equal to mu2 and all the other number to be 1 minus mu2 and 0. And of course, but there's some other case, S1 equal to mu1, S2 equal to mu2, and then you take all the other numbers to be either 1 minus mu2 or 0. And Samuel's conjecture that the minimum is just the minimum of all these polynomials of, or not polynomial, all these functions of mu1 to mu n. And this is still open, and he only solved it for n less than or equal to 4. This will improve the Feiger's result, and it will also, so if we know this for every n, it will solve this problem of finding the threshold of d degree to guarantee that there exists a perfect matching hypergraph. Yes. So in that case, we don't have this, the middle cases. We will go directly to the end when everything is equal to, when they're all equal, have equal distribution. So I think this is also interesting open problem. And also the biggest question is, can we prove this conjecture? So I think in order to show it for this range, it might not be too difficult. The problem is when it's approaching to the other construct, to other bound. So how do we do this case when this is a clique? Remember that even for some other set system problems, it's often more difficult when the extremal case is a clique rather than this kind of structure. You can also reduce it when every random variable is concentrated at 2 points. But then it becomes a real optimization problem. We don't know how to solve it.
So Feiger's result also, like, you can always reduce third and involve the 2 points.
Yeah. And that's not indeed not so difficult. And the last thing is, like, for this, for the second model of distributed storage system, can we solve it? Second distributed storage system. And okay, I think it's just 12:30, so I'll stop here. So, thank you.